Hi, welcome to another video of Intro to Machine Learning. In this video, we are talking about ensemble learning in general, random forests in specific, and some of the training techniques that are used to train random forests, specifically bagging and boosting. And finally, we'll see a complete Python implementation. Okay, so the idea of ensemble learning comes from probability, the law of large numbers, if you're familiar with it. An example to demonstrate that is, let's say we are interested in calculating the average of 100 numbers, and let's assume those numbers are from 1, 2, and so on to 100. Also assume, let's say I don't have the resources to pick up every number and calculate the actual average. So what I'll do is I'll randomly sample some numbers from it. If I picked up two numbers here, I'll calculate the average, which comes out to be 67.5. And so this is my estimated average. Right? This is my estimated average for all these 100 numbers. If I continue to take random samplings and keep increasing the number of values that I'm picking up, so instead of 2, I pick up 5 and 10 and so on. If I go up to 20 variables and pick up randomly like 20 values and average them, the average will keep shifting towards the true average of all these 100 numbers. That is the basic idea behind ensemble learning. And instead of these numbers or these values, we apply it to the different predictors. So if we aggregate the predictions of a group of predictors, meaning classifiers or regressors, or in more simple terms, different algorithms, let's say, right? You will get a better prediction as compared to an individual predictor like we've been doing until now. A group of these predictors is defined as ensemble, and obviously this set of methods where we are combining more than one algorithm is known as ensemble learning. A few more details about ensemble learning. This, as the definition suggests, it consists of aggregating multiple outputs made by a different set of predictors to obtain better results. This set of algorithms, I would say, rather works best when the predictors are independent from one another as possible, and there are techniques to do that, because we don't want any kind of correlation between the different predictions that we made, because then it's almost useless, right? So one way to get diverse classifiers is either to train them using different algorithms. For instance, I can train the same data using, let's say, logistic regression, right? Or decision tree, and then maybe SVM and so on, right? Whatever algorithms we are familiar with. And then we can see, let's say if this was a classification problem and there were two classes, whether a particular training point, test point belongs to A or B. Let's say linear regression, logistic regression predicted A. So this is one vote. And then decision tree and SVM predicted this. We'll take the majority vote. Some kind of like this process, right? And training them on different algorithms could be a solution to that. Because this will increase the chances that we'll make different types of errors. Each algorithm has a different type of error associated with it, but the overall accuracy when we get this kind of an arrangement improves the overall ensemble's accuracy. So that's the general idea behind it, and I'm just giving very basic notion about ensemble learning. Okay, so one such algorithm is random forest. What random forest does is it does not use different algorithms, rather it uses the same decision tree classifier, right, on a different random subset of the training set. If, for example, I have this training set where I have line 1, line 2, these are observations, right? What I'm going to do is I'm going to pick up, let's say, observation number 1, observation number 3, and some observation number 9. And I'm going to train my model. So this is going to be my first training one. And then again, I'm going to pick up, let's say, randomly 2 and again 3, maybe, because there can be a repetition, that's fine. And maybe 8, right? And that's going to be the training 2, which is the second model. So these are individual decision trees. And then similarly, I can randomly keep getting a subset of the training set and keep building decision trees on them. So that ensemble of decision trees is known as random forest. Random forest is an example of an ensemble learning technique, right? So this is one way of doing it. I'm not using different algorithms. I'm using the same decision tree algorithm, but on different subsets of the training data. So this is what random forest looks like. Obviously, this tree will give us some output. Let's say I'm doing, again, A and B classification. This gives me an output of class A. This gives me an output of class B. This gives me an output of class B for some test set, right? For some point in a test set. So the way to get the final output is that I'll see which one is the majority class here out of the output of all these entries. And based on the majority, I'll get the final class, which in this case is obviously B. There are two types of voting that happen. One is known as hard voting and one is known as soft voting. Again, not to go into too much detail, but still, let's say we have like three things here. For instance, class A, class B, class B, and this one has a probability of, let's say, 0.90. This has 0.45, this has 0.45. And so here, according to hard voting, it will classify as class B because I have a majority vote. In case of soft voting, what will happen is that I should calculate the average of all these probabilities, right? Essentially, like all the trees must have given out some probability value. And based on that, I'll decide which class my final test point that I'm testing belongs to. So that's the slight difference between hard and soft. Okay, so that was about how random forests look like, what is the basic structure, how they are trained. They are trained using a bagging method. This is known as bagging, the method that we use for training them. It's like the full form is bootstrap aggregating. It consists of randomly sampling subsets of the training data, as I said, right? Randomly getting a subset, fit a model, get an output, get a prediction. Um, so now, for example, an initial training data set has had n observations. In bagging, we'll create multiple training data sets of size n by sampling uniformly with replacement. This is an important aspect. And so like some points can get repeated, right, in each of the trees that we saw earlier. We can have the same observation repeated in multiple trees. Okay, so then we build classifiers on each bootstrap sample, as I said, and we take a majority vote. Now this can arise, right, since some of the newly created data sets, because these are like subsets of the original data set, can have repeated instances of the data, we know that, right, or missing some records altogether. And so some of these trees will give really bad output as compared to, like in terms of the accuracy, as compared to that classifier, that single classifier that we could have built on the entire training data. So this is known. But how is this better than that like single classifier that could have used the entire raw data? It is better. Why? Because it reduces the variance of individual classifiers. So we are taking together everything, right? So that improves our general error. Now, the increased accuracy from bagging, as I said, comes in because of the reduction in the variance as compared to a single classifier. And also, we are resampling the data with replacement. So, bagging is not focusing on that one specific data instance of the training data, right? So, we are less prone to overfitting, which is again a big advantage of bagging. Okay, there is another method that's also used for training random forests that's called boosting. It's slightly different in the sense that this is more sequential. If you think about bagging, that's parallel, right? Because we have these parallel subsets that are working and then we are getting a majority vote. Here, this is more sequential in the sense I'm going to take, it's an iterative methodology, right? So basically, I have weights that are applied to certain observations. Why are those weights applied? Let's see. So what happens is these are different iterations that will happen. We will start with all the data, right? Uniform distribution, everything has equal weight, and I'm going to train my data. And then what will happen is some of the observations will be misclassified, as we have seen in our confusion matrix before. So I'll focus now on those misclassified points. And those misclassified points in the next iteration will have a higher weight because then I'm focusing on them. I really don't want them to be misclassified again, and so on, right? So I'll keep continuing with the same data set going through like multiple phases. So that's why this is a more like a sequential sort of technique, right? So this is called boosting. This is another technique. Definitely, scikit-learn provides us with bagging and boosting classifiers. We can utilize them the way we would like. But now we're going to look at the Python implementation of the random forest classifier in scikit-learn now. So let me keep this and go to Python. Here we have the code random forest classification. Obviously, I'll be posting it and providing the link in the description below. So I'm again using the social network ads. Remember when we were estimating whether a person is going to buy a product or not, right? And we are given the age and the salary. So here is the CSV file. This is all what we've been doing until now, right? Train, test, split, feature scaling, all of that stays the same. The thing that has changed here is this. So again, if you're looking at a classifier in scikit-learn, the thing that I did was just go ahead and Google it, and I found this random forest classifier, right, in the scikit-learn ensemble package. So that's exactly what I'm doing here. I'm importing it from scikit-learn.ensemble and creating an instance of this class random forest classifier. Notice I'm using n estimators equals 10. This is how many trees do you want? Like what is that n that you want in your classifier, right? So I could have it as 20. And then the criterion is entropy. So remember the information gain criteria. So that's what I'm having here. And this is random state equals 0. And I'll create this classifier and predict values for certain things. So I'll predict for that 1 point. Remember that we've been predicting throughout that if the person's age is 35 and the salary is 100K, whether the person is going to buy. So this says yes. So most of our classifiers have said yes, except for one, I remember. And then we can predict the test results and see the accuracy for this particular. The accuracy is 0.92, which is pretty high, right? Let me save this and I'll provide this code. I have another code which is called compare classifiers. I wanted to show you here that with scikit-learn.ensemble, we have something called a voting classifier. So what this does is it is going to create whether hard voting or soft voting using different algorithms. So this is like more in terms of like you can do ensemble learning yourself using this voting classifier. How you have to do it is rest of the steps stay the same. I'm doing a test train split. I'm doing feature scaling, all of that. But here I'm calling like 3 different algorithms, right? So logistic regression, random forest, and SVC, which is support vector classifier. And using this voting classifier, I'm creating another instance. Notice it takes estimators as a parameter in a list of tuples. So here in the list of tuples, you have to provide which models do you want. So this goes back to our initial discussion of ensemble learning when we said we can use different, here, let me go back and show you, where we can use different models altogether. Instead of like having only decision trees, I can have logistic regression here, I can have decision tree here, I can have support vector machine here, and so on, right? So that's an additional step that I'm showing you using this. And here, finally, I'm printing the accuracy score for each model, including the voting model. And notice like voting is hard. Why? You know already. You can also select voting equals soft, but be a little more careful with the support vector classifier because that might give you an error. So I would recommend let's keep it to voting equals hard, right? Okay, so let's actually run this and see how the voting classifier works. Okay, so this is more about my setup of Anaconda, so just ignore that. Here you can see the voting classifier gives me the highest accuracy, which is 0.94. SVC and random forest give me 0.93 and logistic regression give me 0.89. So that clearly tells me that this really helps if I'm using different algorithms and then getting the highest majority voting. So this is another way of implementing an ensemble learning technique. So the 2 things that we learned today is that ensemble learning can be combining different predictors and then getting the results like we did with the voting classifier, or you can have all like different types of trees using random forest classification, right? To have trees as different predictors and combine the output of trees. So that's it in this video. That's about it. Thank you.